Okay, Michael, what's your answer?
All right. So, again, a lot feels like a good answer. It's already written down on the left. But it's also, maybe we can quantify this. So, if it were, maybe one way to think about this is if each of those empty boxes there is either true or false, it's kind of like a bit. And we're asking how many different bit patterns can we make? And in general, it's 2 to the number of positions. But here, the number of positions is 2 to the n. So it ought to be 2 to the 2 to the n, which is that the same as 4 to the n?
No.
Okay.
But you're right. It's 2 to the 2 to the n. So it's a double exponential, and it's not the same thing as 4 to the n. It's actually 2 to the 2 to the n. Now, how big of a number do you think that is, Michael?
I'm going to go again to my go-to place and just say a lot.
It is, in fact, a lot. And I'm going to look over here, and I'm going to tell you that for even a small value of n, this gets to be a really big number.
So for 1, it's 2 to the 2 to the 1, which is 4. That's not a big number.
That's true. What about 2?
For 2, it's 2 to the 2 to the 2. So 2 to the 2 is 4, so it's 2 to the 4, which is 16.
What about 3?
All right, so that's 2 to the 8th, which is 256.
Mm-hmm. So that's growing pretty fast, don't you think?
Sure, but those aren't big numbers yet.
What if I told you that for n equals 6, 2 to the 2 to the n was, I'm going to start writing it, okay?
Ready?
1, 8, 4, 6, 6, 7, 4, 4, 0, 7, 3, 7, 0, 9, 5, 5, 1, 6, 1, 6.
Holy monkeys.
Yes, that is in fact the technical term for this number. It's a holy monkey. It is a very, very big number. So 2 to the n grows very fast. We already called that evil. 2 to the 2 to the n is a double exponential, and it's super evil. It grows very, 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 very fast. So what's the point of this exercise, Michael? It's to point out that the space of decision trees, the hypothesis space that we've chosen, is very expressive because there's lots of different functions that you can represent. But that also means we have to have some clever way to search among them. And that gets us back to our notion of an algorithm that's actually going to very smartly go through and pick out which decision tree. Because if we aren't very smart about it and we start eliminating whole decision trees along the way, then we're going to have to look at billions upon billions upon billions upon billions upon billions of possible decision trees.